Hello learners, I welcome you all to this online session on Zenithal Projections and although I have mentioned part 1 but I'll try to cover both part 1 and part 2 in this session, and in the next session I'll take up some other topic. So after viewing this video program, you should be able to define zenithal projection and list its basic properties. Divide the zenithal projection on the basis of position of tangent plane and on the basis of placement of light source, and illustrate the construction of zenithal mnemonic polar projection, zenithal stereographic polar projection, and list the properties of zenithal mnemonic polar and zenithal stereographic polar projections and differentiate between them. So in the previous sessions we have studied about map projections, and we have studied about conical projections in general, and three types of conical projections with one standard parallel, two standard parallel, and bones projections. We have already done the graphical construction of these projections. But for those who missed the previous sessions, just a basic introduction to map projection I'll give. Now, what is map projection? Map projection is a network of graticule graticule of latitudes and longitudes when they are transferred from Earth's three-dimensional ellipsoidal shape of Earth to a two-dimensional plain paper. So basically we try to flatten the three-dimensional Earth into two-dimensional projecting surface, and that is map projection. And how do we divide this map projection? On the basis of projecting surfaces, as I have already told you, you can also see in this figure there are three types of projections based on the projecting surfaces. Now I have a spherical ball over here and a paper which I am assuming to be a projecting surface, and I am rolling the paper in the form of a cylinder, and I am placing the Earth which is in the form of this ball, I am assuming, and if I am placing this Earth in the center and this paper has been rolled in the form of a cylinder. So when the graticules or the network of latitudes or longitudes are transferred on this paper, we roll it open and then we get the graticules as we show in this figure also, like cylindrical projection, and when we open the cylindrical surface we get the graticules in the form of this. And when we have the paper in the form of a cone and we place the globe in between here over here, then it is this paper or the is tangent to any particular parallel in the globe, and that is the standard parallel, and which we have dealt with in the previous sessions, conical projection with one standard parallel. So in this way, if the projecting surface is in the form of a cone, it is a conical projection, and if the projecting surface is in the form of a plane which is tangent to the globe, touching the globe at a particular point, maybe North Pole, South Pole, or any point along the equator, then it is called a planar or a zenithal projection. So in this session we are dealing with zenithal projections, and two types we are dealing: zenithal mnemonic polar case and zenithal stereographic polar case. Now let me also have a quick recap of how we divided projections on the basis of qualitative attributes. Now when we are transferring the three-dimensional Earth, the graticules of three-dimensional Earth on a two-dimensional surface, then we are not preserving all the properties of the three-dimensional Earth. So we are in some cases only the area is preserved, or in some cases the shape is preserved, or in some cases the direction or the true bearing is preserved. So if a projection is preserving the area or representing the true area of the globe, it is called equal area or homolographic projection. If it is representing true shape, then it is called orthomorphic projection, and if it is showing showing the correct bearing or direction, then it is called azimuthal projection. And now based on the source of light also we have projection based on the use of light. Also we have two types of projections: perspective, when we use light for projecting the meridians and parallels, then it is called perspective projection. And when we are not using light for projecting the graticules of meridians or latitudes, then it is called non-perspective projection. Now coming on to this session, which is specially on zenithal projection. What is zenithal projection? Just now I have told you that the paper is tangent to the globe. This way, if it is tangent to the globe, then it is called planar or zenithal projection. And there are perspective zenithal projection uses the light as a source for projecting the graticules. So and based on the source of light, again position of the source of light, there are three types of projection. You can see in this figure, when the source of light is in the center of the globe, it is called mnemonic. When it is diametrically opposite to the projecting surface, this is the projecting surface, and the source of light is diametrically opposite to the projecting surface, then we get the graticules in this way. The network of latitude and longitude. When I say graticule, it is the network of latitude or longitude, or network of parallels and meridians. We get it like this. And when the light source is coming from infinity, we get the graticules like this on the projecting surface. And you can also differentiate between the three, like based on the increasing distance from between the meridians or parallels, or here you can see that the distance between the parallels is decreasing in case of orthographic projections. Now in this each of these three types of projection is also divided into three more types based on the positions of the tangent plane. Now if the tangent plane or the projecting surface is situated on any of the two poles, then it is called polar projection, polar case of zenithal projection. If it is touching any point along the equator, then it is called equatorial case. And if the tangent plane is touching any point between the pole or equator, it is called the oblique case of zenithal projection. So we have altogether 9 types of perspective zenithal projections: mnemonic zenithal, polar equatorial oblique case, then stereographic zenithal, polar equatorial oblique case, and orthographic zenithal, polar equatorial oblique case. Now coming on to the two types which I am going to deal with in this session is zenithal mnemonic polar case. We can very well define this like zenithal, it is a zenithal projection; mnemonic, that the light is kept in the center of the globe; and it is polar case because the paper or the tangent plane is touching either of the two poles, either north pole or south pole. Now if we get a question, now I must tell you that this topic is related to our course BGG-CT 133 core course of general cartography, and BGG-CL 134 core course of cartography practicals of BSc general program. So in the practical session also you can get questions like construct a mnemonic polar projection for northern hemisphere where RF is 1:3:320 million and interval is 15 degrees. So in the previous sessions I have already dealt with this RF. This is the representative fraction, and 1 units on map represents 320 million units on the ground. So in this question RF is 1:320 million, and as I have already told you that radius of earth is 6,400 kilometers, and when we convert the kilometers to centimeters, we get 640 million centimeters. Now radius of the reduced earth would be 640 million centimeters divided by 320 million centimeters, which will be equal to 2 centimeters. Because you know 1 unit is represented by 320 million units, then 640 million units would be represented by 2 centimeter on the map. Now if we construct a circle of radius 2 centimeter, and then in the question we have been given that the interval is 15 degree, that is the interval between the latitudes and between the longitudes is 15 degrees. So we draw 15 degree, 30 degree, 45 degree, 60 degree, 75 degree and 90 degree parallel, and we project it. Since light is kept at the center of the globe, it is a mnemonic case. So we project the lines on the plain paper, and so we can see that 15 degree north latitude is projected over point A, 30 degrees projected over point B, 45 degrees projected over point C, 60 degree at point D, 75 degree at point E, and North Pole is projected at point F. And with the help of this graphical construction, we get the radii of all the parallels. Like FE represents the radii of parallel 75 degree north latitude. So FD represents the radius of parallel 60 degree north latitude, and similarly FA represents the radius of 15 degree north latitude. You can see that equator in this case is not projected because it is projected to infinity, it is parallel to the projecting surface. So it is one demerit of this projection that we can't represent the entire hemisphere in this projection, as equator is not projected in this projecting surface. Now with the help of all these radii, we FE, FD, FC, FB and FA, we construct the circles, and you can see that all the parallels are represented by concentric circles, and then with the help of protractor we draw all the meridians, and these are drawn as straight lines radiating from the center. And since the interval is 15 degrees, so this is 0 degree, 15 degree, 30 degree, 45 degree, 60 degree, 75 degree, 90 degree and so on till 180 degree, and this is the western meridians which are drawn as 30, 60, 90 and in 15 degree intervals. So in this way graticules of this projection is drawn. And now coming on to properties of zenithal mnemonic polar projection, we can see that the parallels in this case are concentric circles, and distance between the parallels is increasing from the center, so distortion is more away from the center. Similarly, meridians are straight lines radiating from the center. Distance between the meridians are also increasing from the center. However, the meridians are actually they are great circles, and their planes are cutting through the center of the globe. So any straight line drawn on the map is the shortest distance. So this is correct. One important property of this projection, that it is showing correct direction, and any straight line drawn on this projection is the shortest distance between two places. And the scale gets distorted away from the center. This is the reason it is suitable only for small areas, like from polar regions to around 60 degree latitudes, whether it is north or south. So from polar region to 60 degree latitudes, it is convenient to show in this projection. Entire hemisphere cannot be shown in this projection. Now coming on to another type of projection, which is zenithal stereographic polar case. You can very well define this projection also. Since it is written here zenithal, it means that the paper or the projecting surface is tangent to the globe, and stereographic, then it means that the source of light is diametrically opposite to the tangent plane, and it is a polar case. Then it means that it is touching either of the two poles, whether it is north pole or south pole. And I'll show you how an entire hemisphere can be represented in this projection. If we get a question like construct a stereographic polar projection for southern hemisphere, where RF is again 1 is to 320 million, and the interval is 10 degree in this case. Then as in the previous example also we show that when 320 million units is represented by 1 unit on map, then 640 million units would be represented by 2 centimeters on the map, because 640 million centimeters is the radius of Earth. And then the radius of reduced Earth would be 2 centimeters again, and then we draw a circle of radius 2 centimeter, and then since the interval in the question is given as 10 degree, then with the help of protractor we draw 10 degree latitude, 20 degree, 30 degree, 40 degree, 50 degree, 60 degree, 70 degree, 80 degree and 90 degree latitudes. And then light source is kept over here. You can see S is the source of light, and this is N is the south pole in this case. Then source of light is here, and then you can see that equator or 0 degree parallel is projected at point A, 10 degree parallel is projected at point B. We draw a straight line from the source of light connecting the parallels, and we get the projected meridians at point A, B, C, D, E and so on respectively. Now similarly, as in the previous case, we get the radius, like Ni is the radius of 80 degree south latitude, Nh is the radius of 70 degree south latitude, and again 30 degree consider this it is projected over point D, and Nd becomes the radius of 30 degree south latitude. And then we construct again the concentric circles with the help of the radius received from here, and we can see that 10 equator is also projected over here, and 10 degree, 20 degree, 30 degree, 40 degree, 50 degree, 60 degree, 70 degree, 80 degree, and this 90 degree south is in the form of point over here. So all the parallels are drawn as again concentric circles in this case, and the meridians are straight lines radiating from the center. We draw the meridians with the help of protractor with 10 degree intervals, like this is 0 degree, and then 10 degree, 20 degree, 30 degree, 40 degree, 50 degree, 60 degree, 70 degree, 80 degree, 90 degree and so on till 80 degree, and then these are the western meridians 0 to 180 degrees. So it's very easy to construct both these types of zenithal projections. Now coming on to the properties of zenithal stereographic polar projection, we can see that parallels are also concentric circles in this case, and distance between them increases away from the center. But this increase in distance is lesser compared to the previous case. Like in the previous case we saw, I am showing you this figure, this distance between the parallel is more in this case. So there is less exaggeration in this case, and you can see distance between meridians are also increasing as we move away from the center, but this increase in distance is proportionate to the increase in distance with the parallel. So there is one important feature of this projection, that it since the increase is proportionate, so correct shape, true shape is represented in this projection. So this projection is also orthomorphic. So the property of the shape is preserved in this projection. So apart from azimuthal, this is also orthomorphic projection. We already studied that meridians are straight line radiating from the center, and the scale has true bearings from the center. So this is also azimuthal projection, like all zenithal projections are. And because of this property, it is used for navigational purposes, and we have seen that the equator is also projected in this projection. So entire hemisphere can be represented. This is the equator part which is projected, so entire hemisphere can be represented in this projection. So it is definitely an improvement over the previous type, like zenithal mnemonic polar projection. In this video program, we studied about the two main zenithal projections, and we studied the graphical construction of zenithal mnemonic polar projection, zenithal stereographic polar projection, and we can now differentiate between the two projections. And we also studied the properties of both these projections, and we had a recap of the previous session also, like projection, how to define projection, and how to bifurcate the projections on the basis of projecting surfaces like cylindrical, conical, planar or zenithal, and how we divided the zenithal projections into perspective and non-perspective, and what are the different types of perspective projections based on the position of source of light, which is at the center, and which is at the stereographic case, diametrically opposite to the tangent plane, and again when the light source is coming from infinity, that is the orthographic case. And we also studied based on the position of the tangent plane also, we divided the zenithal projection into three types, like polar case, when the tangent plane is kept touching any one of the two poles, and equatorial case when it is touching any point along the equator, and oblique case when it is touching any point between the pole and the equator. So learners, in this session only I have completed both the zenithal projections. So on Monday session we wish to take up some other topic, maybe cylindrical projections. So keep watching, and in case you have any doubts, then you can always write to us at satyaraj@ignou.ac.in. Thank you.